Welcome to Spring LIB.
And we're given a relationship between the angular acceleration of a shaft and the angular velocity. That is, the angular acceleration is minus 1/2 the angular velocity. And we're told that at t equals 0, the angular velocity is 30 radians per second. Again, we can write the angular acceleration in terms of the angular velocity and the time and the derivative of the angular velocity with respect to the angular displacement. And then we can, substitute this into here, separate variables, and integrate. And so we get an integral from 0 to theta of minus 1/2 d theta bar equals the integral from 30 to 30 radians per second to 0. Because we're looking for the number of revolutions shaft will execute before it comes to rest. And so we're looking for when it comes to rest here, d omega. And we can, this is all nice because omega cancels out here. So everything is very easy. And we can just simply plug these things in and we get theta equals 60 radians or 9.55 revolutions. So that takes about 9.5 revolutions before it comes to rest. Now they ask us for the time required for the shaft to come to rest. Okay, so so again, this is a little bit interesting problem because you see that you have some revolutions where it comes to rest, but when we integrate this, so we know that omega or alpha equals d omega dt, right? This is just the angular acceleration. There's the time derivative of the angular velocity. So we get this equation here. Again, separating variables and integrating, we get an integral from 0 to t dt bar equals the integral from 30 to 0 of minus 2 over omega d omega. Now the issue here is that this becomes a natural log, right? And evaluating the natural log at 0, the natural log of 0 is minus infinity. So what this tells us is that it takes infinite amount of time for this for the shaft to come to rest, although it has a finite number of revolutions, which is interesting, right? That it has a finite number of revolutions, but an infinite number of time. Now we can, again, this is a differential equation that you could solve because we have, in fact, it's omega dot equals minus 0.7 omega. And again, you could solve that if you have had a different equation in class of differential equations and get the exact solution for what omega is. Now they ask us the time required for the angular velocity of the shaft to reduce to 2% of its initial velocity. So 2% of this is 0.6 radians per second. And so now we can plug that into here instead of 0. And so now we get the same integral, but we have different bounds here. So now we get minus 2 natural log of 0.6 over 30. And that is, we can calculate that, and that's 7.82 seconds. So we can see that it takes, to get to a very slow speed, about only 2% of what it originally was, it's about 8 seconds. But to actually get down to 0, it takes an infinite amount of time. So it's basically exponential decay. So it and it never reaches 0, but it slows down fairly rapidly and gets to practically 0, after about 8 seconds.